But today we are going to talk about these ones, which form essential component of the hydrogen supply system.
Okay. So to have the opportunity to reduce the costs.
All right.
And
okay.
this pressure can damage your fuel cell.
Okay. So you're saying, Waldemar, that this is where the vroom vroom comes from.
Yeah, it is.
Fuel cell systems usually run at 1.5 bar, but the hydrogen is stored at pressures 500, 600, 700 times higher than that which is running at a hydrogen system or the fuel cell. How do you make that work? And that all in a jittering vehicle even. It's a big question which we're going to talk about today. It's all about hydrogen supply systems. My name is Steven. Welcome to Hyfindr Tech Talks. And today I'm joined by an expert in this field. He comes from Poppe Potthoff, which is a company dealing with fuel supply systems and things in the mobility area. He is a senior technical manager there and has worked on these topics for years. I'm very pleased to welcome Waldemar Raskop.
Thank you. Thank you very much to be here and for the invitation.
Well, Waldemar, it's great you're here. We're going to pick your brain on hydrogen supply systems. So I want to start. What is a hydrogen supply system?
So the hydrogen supply system is a system including some components that allow you to distribute the gas from A to B. Means from the receptacle, from the tank receptacle where the gas is flowing to the vehicle, then through the lines and the distributing systems to the tanks.
Okay.
We can see it here on our demonstrator. So that show you how the gas is flowing into the tanks. It's storage in the tanks at 700 bar or 350 bar, depends on the application.
Yeah. So this is essentially a diagram where you have the consumer.
Yeah.
Yep. And then, so, all these systems in between. Obviously, the tanks here.
So we see here the tanks.
Are these,
The tanks, the on-tank valve and the end plugs. And the pipes, the parallel charging unit. Or it's sometimes also called as manifold.
Manifold, okay, this one, yeah.
So, and the high pressure regulator unit, the HPRU.
Okay, so these are essentially, we have been fortunate to talk about this on-tank valve with one of your colleagues who did an excellent job. I think it's another video. But today we're going to talk about these ones which form essential component of the hydrogen supply system.
Yeah.
And I see you also brought them with you here.
Yeah, sure.
So maybe we can take them through one by one.
Of course. Yeah. So at first, when the gas is flowing to the tanks, it passes through the lines.
Okay. So this is just it's a hydrogen fuel line, like this.
It's a hydrogen fuel line. It's a high pressure line made of BPH2.
What is BPH2?
BPH2 is our material that is chromolybdene based. That's known from decades in the hydrogen field. Okay. It's an alternative material to the stainless steel.
All right. Okay.
So to have the opportunity to reduce the costs and some benefits to the
cheaper
system.
than
cheaper than the stainless steel. Yes.
Okay. And the obvious question: embrittlement, all these kind of things.
Don't worry about that because it's chromolybdene based. The ground material itself is using for decades in the hydrogen world, and we did a lot of tests to avoid or to bring the customer the information that it's safe.
Okay, all right, okay. So this is, let me say, the piping here, but then also this piece.
This piece is a parallel charging unit.
Parallel charging unit. Okay.
Yes. So
that's you call that the
earlier
you called that the PCU all the time. I'm
PCU.
happy you're calling it its real name now.
Yeah.
Parallel charging unit.
Yeah.
Why parallel?
Why parallel? Because you have several kind of connections. There you connect the pipes, and these pipes is going to the tanks.
Yeah.
And you can fill the tanks in parallel.
Okay. All right.
So it's divide the stream into some upstreams.
Okay.
And
So
that allow you to fill the tanks faster.
Okay. So essentially this would connect onto
This
here.
would connect to the parallel charging unit.
Yeah. Okay.
So as you want, you can do it by yourself.
Okay. So,
or I help
yes,
you.
yes,
So
yes, please.
means we place the switch head into the cone,
Yes.
and then just screw the nuts to the connection, and then position the pipe
Okay.
into the right way,
Yes.
because this joint allow you to compensate tolerances in the system.
Ah, okay. Yes, and I just need to switch here because I know we had a nice diagram that also showed this. Yes, this is the one. Yeah.
So this is what we are talking about.
Ah, okay. So this is actually what we just did here now. So
Yes.
it's nice that we can see that there.
Yeah.
It's this
The-
way around.
this way,
Exactly.
yeah.
Okay.
So we have the pipe.
Yeah.
This the switch head.
Yes.
This is sphere interface, and the opposite is connector or adapter with an cone interface.
Okay.
So means
okay.
I have a sphere in the cone
Yeah.
that allow you
To move
to
this.
move this.
Ah, right. Okay. So that's what we see here. You know,
Yeah.
up to 3 degrees. Yeah. Okay.
yeah, 3 or even more if you have another interface.
I see you can also put a check valve
Yeah.
and then that. Okay. So you
So-
basically you can.
So the parallel charging unit is a modular system.
Yeah.
It's a system itself
Mhm.
where you can place pressure sensors or temperature sensor on it or check valve. It depends on the.
Yeah, I see. We also have a pressure sensor right here. Huh?
Yeah.
This is the one. Okay. So that will also get the pressure right. Okay.
Yeah.
So that means now we've done the connection, and I think this is really interesting because it has this special endpoints. I'm just gonna get this unwound here. Yeah, exactly. And I think that was what you were saying earlier here.
Yeah.
Where we can see
So-
that.
So you can see the sphere and the cone, and how it's working through the mounting process. You put the pipe into the interface or into the joint, and then you can place it in the system to avoid stress in the system. Because
Okay,
stress and vibrations bring your joints to crack.
All right.
And
So that means that.
that's
So
avoided.
just gonna move this here a bit. So that means we can put that there, and that can still move around a bit. Okay. Does that do that? I mean, like you put it on, and then it continues to move in the vehicle, or
No, if you tie it,
Yeah.
then it's absolutely fixed.
Okay.
And it's vibration proof because it's coming from the diesel technology, and we have experience in this interface since decades.
Yes,
So-
exactly. Yeah, that's Poppe Potthoff. Yeah. Is this the same material as this?
Yeah, it is. It
Okay,
is. It's also PPH2 material, and as I said, it's our own material that
Okay.
is.
So that means coming from the tanks, you now have this. Okay. So let moving on. Let's see. So now we've had a look at this, the PCU charging unit.
And then we're going to the consumer
Yep.
in the system, and here
Yeah. This is the next part.
next component what we will talk about.
Exactly. And
is
that is this one, right?
This one, yeah.
Yes.
It's a HPRU, high pressure regulator unit.
Okay.
So it's a combination of several kind of components itself. So we have the opportunity to have a service interface, also an pressure relief valve, and other components that can be placed into the unit itself to reduce complexity of system and joints, number of joints.
Okay. So just to order this here now, this is coming from the tanks, right there. Okay. And then, so that's coming in here.
It's coming here.
Yeah.
It's flowing through the valve here. It's a piston.
Yeah.
Then through the or to the proportional valve.
Okay, there's a proportional
so
valve.
It's a proportional valve here, and
okay.
then it's controlled by proportional valve. Then the gas is flowing from the pressure reducing chamber to the outlet.
Okay, this is, I think, the solenoid. No,
It's a proportional valve.
It's a proportional valve. Okay.
So the component itself is electronical control.
Ah, it's a control. Okay.
So you need an ECU or TCU, tank control unit or engine control unit, that give you the PWM signal to this component
coming in this way. Okay. And so that means the consumer is here.
It's here, yeah.
Yeah. Okay. Cool. So in here, consumer here, sensor here.
So we have pressure sensor, high pressure sensor. Maybe we can switch to the.
Yes, we had that. Yeah. Ah, okay. There you go.
So here we can see better. So which components are in the HPRU and how it works. So we have here an inflow into the component through an 10 microns filter.
Yeah.
The filters are necessary in our.
Okay, so there's a filter in there.
There is a filter inside.
Okay.
Because particles and dirt is
a topic.
It's a topic in the systems.
Okay.
So and therefore we have a filter inside. Then the gas is flowing. So proportional valve. So we have a temperature sensor to control the inlet gas temperature. Also the pressure. Then the pressure in the or temperature in the low pressure area to see how the temperatures are growing or decreasing.
Yeah.
And then also the low pressure sensor, and then out to the consumer.
Okay. And you mentioned, and this is a service interface.
Yeah, this is a service interface unit. It's
what is that used for?
Normally it's a standalone component. The component is needed in the system to for maintenance reason, or
you want to let out all the gas or whatever.
The gas, or you have to clean the low pressure area after some maintenance.
Okay. And it says it has a burst
disc. So the burst disc is an optional component that is necessary, and is also was implemented after the market screening and also from the customers, from our customers, that if you are using components that are electronically controlled, then you are running into the safety analysis and as a level of the vehicles.
Yes.
And then it can be high or low risk of some accidents and so on. So, and you have to cover up the risks. And if you are using only electronical devices, then you have to write software solutions, and that is really, really tricky and complicated. That's why it's a better way to have some mechanical things that reduce the risks, and you have no issues with your following.
So it's part of a safety and
it's a part of the
system basically, and that would also go to an appropriate outlet.
Okay. And then you have also the pressure relief valve that also gives
so you have a burst disc and a pressure relief.
A pressure relief valve. Yeah.
Because are they on the high pressure side?
No, on the low pressure.
On the low pressure side.
On the low pressure side, because the systems are never tight. So in the norms and standards, you have an allowedness of leakages.
Yes.
So, and sometimes you have some failures in the system, or something goes wrong, or the vehicle is stay overnight or weak.
Yes.
And then through the leakages, sometimes you have some pressure increasing in your low pressure side.
All right.
And this pressure can damage your fuel cell or the following components.
Yes.
So that's why you need a pressure
better to
relief
take
valve.
them out there. Okay.
Yeah, you have to.
Right. Okay. The pressure relief can open and then close, but the burst is once burst.
And if it's burst, it's burst.
So
but it's a worst case solution if everything in the system is going burst. Means we have a wrong signal from the control units, tank control or engine control units, and all the valves are open, and you have a full load of pressure and mass flow through this system. So and the pressure relief valve is not able to bring all these mass flows out,
Okay.
then the pressure is increasing and you have to bring it out.
Okay.
So then
that comes
you have to activate the burst disk.
How many times have you seen it activate?
Never.
Never.
It's absolutely worst case scenario.
Okay.
And it's coming from the failure analysis and so on.
Okay, safety.
What is if.
Okay. Cool. So, I know we've talked about several components now. Actually, it's surprising that we only have, let me say, two, this the parallel charging unit, the pipes, and then this. So two, let's say, bigger units, other than the on-tank valve. How does this work in terms of the flow? And I know that with this you are covering a wide range.
Yeah, we are covering a wide range because the main reason why we started the development of this component is that we did a benchmark analysis and saw that there are a lot of solutions in the market how you can decrease your pressure in the system.
Yes.
So the first one is a dual stage system where you have an electronical pressure regulator directly on the tank rack to reduce the pressure, then to a middle pressure, then also to have an electronically controlled pressure regulator directly on the HICE, on the hydrogen combustion engine, or also on the fuel cell. So the next solution or the next option is to have a mechanical reducer, and then to have an electronically controlled one. So, but what we see now, and also in the future, and lessons learned from the CNG applications, that these two options is not really necessary.
Okay.
You can run it by one component and combine a lot of things, what I described before, further. That you go directly to the consumer with one component to reduce costs and joints.
Okay. So I think worth mentioning is that, I started this video by saying that we're talking about fuel cell system, but you are actually offering a solution not only for fuel cell systems here, but also for internal combustion systems or any other form of consumer that needs less pressure than what is in the tank.
Yes.
And so what I understand here is that you're essentially reducing, so you could have this and that, and then go into there. But what you've done now is with this one component, you're basically just reducing the number of things. So basically you need tanks, a distributing thing here, and this, and then you can go in the system. So and pipes, of course.
Of course.
So keeping
keep it simple.
More simple. I'm personally convinced that that's what this whole hydrogen economy needs. More simplicity, easier components. So actually, it's great to talk with you about this. Okay, but take us a little bit deeper still, because supply is always a thing. So how much flow do you get through there? What pressures can this take?
So then we have to switch to this diagram and see the performance level of these components. So means we can supply to a fuel cell or to a hydrogen combustion engine, a PFI solution or DI solution. PFI, port fuel injection.
All right.
With less pressure. DI is a direct injection.
Direct injection, okay.
And then for the future, also the opportunity for high pressure DIs, where we have injection pressures like 300, 310 bar.
Into the
chamber.
Combustion chamber. Okay, but then your tank still needs to also deliver that kind of pressure. So
about 300.
Okay, because you've not got a compressor on that line, so basically you're always reducing from what.
So we are reducing.
Yeah, reducing. Okay. And so this one component, and I think this is really what's in this one component, can do pressure ranges coming from the high pressure tank system.
Yeah, from the tank.
From the tank,
700 bar or 800 bar.
And you can bring it down for the fuel cell, which would be
around about 5 to 15 bar.
Yeah.
So depends on the fuel cell itself.
Yes.
Then also for the high pressure or PFI solutions from 15 to 30 bar, something like that. And also the DI application that's going to the 60 bar.
Okay. Waldemar, to be honest, I must say, fuel cell operating at 10 bar, don't know if I've seen so many of those. Normally they go lower, you know, at the cell.
At the cell itself.
Yes, exactly.
Because normally you have directly and find those valve.
Yes, exactly.
On the fuel cells. And the next development and the next evolution of this component is to eliminate these find dose valve, to have just one component that fits all.
So this thing would then also supply, I think at this end,
this end,
it would also be able to supply like your 1.2, 1.5, you know, those the operations guys are already having sharp ears here, So this can be this can supply, could at that point supply that already. Can this already do that, or this is something coming?
So it can do that.
Yeah.
We did some tests through our development project.
Yes.
Nemo, Nemobil, founded project.
Okay.
So and the first test show us that we are able to bring the pressure down.
Okay, cool. Well, yeah. Waldemar, I know you also brought some data. So maybe we can, I don't know, we can find that. There you go. Yeah, exactly.
So I brought some data.
Yes.
So this is our diagram how the HPRU works in the fuel cell application.
Yes.
So what the benefit is. So we starting from the 800 bar.
Okay.
And we decrease the pressure nearly to the 0 bar. So, and as you can see here on the outlet pressure graph is that we are really straight in case of reducing pressure.
Yeah, I mean you're between, what is that? This is 9.7 and 9.9 or something.
Yeah. So the
bar. So we have to look at the scale here.
Yeah.
And that's coming down from 800 bar.
800 bar, yeah. So
going down to
and as you can see here, so we have accuracy of the component. It's really high. So we have a deviation that is control deviation that is less than 1%.
Right.
So and the outcome conditions was that the fuel cell or the consumer wanted to have just 1 grams per second.
Okay. So I mean, I need to be. So you're giving through the PWM signal. You're telling this one what outlet pressure you want, and the whole regulation is happening in there. So there's the controller doesn't have to do that.
No.
This is done in there.
This is done. So this component is also the high pressure regulator is controlled by the proportional
valve. Okay.
So, and what we have to do is to compare the data's incoming pressure and outgoing pressure, and then the signal from the engine control unit or from the control unit is telling them what is to do.
All right. Okay. Interesting. I mean, that's like you get like 600 bar difference.
Yeah, or more.
You walk through that, or more. Yeah?
Or more. So and also what is really interesting is that for the consumer itself, we have a nearly constant outlet mass loss.
Yes.
So
Okay.
that is really necessary.
Okay.
So, but that's not all.
Yeah. Okay.
So we have also the tests, and as we said, this component is ready for hydrogen combustion engines, and we tested it. Yeah. So, and this is
what's the difference? Sorry, I just interrupt you. Like difference in supplying a fuel cell and supplying a combustion engine from a supply side.
From the supply side is that the fuel cells are working static.
Okay.
So they need static flow. They are not really dynamic. So they have the dynamics, but it's really low.
Okay.
So, and the combustion engine, that is a dynamic
like a combustion engine, like, you know,
Like-
so
like-
you're revving up and
Yeah, you're
like
revving up.
vroom, vroom,
So
okay.
you need in seconds
Yeah.
the or less than a second the power.
Okay.
So
And this can do that.
and this can do that.
So you're saying, Waldemar, that this is where the vroom vroom comes from.
Come from yeah, it is.
Of a combustion. Actually,
Yeah.
that's interesting because I mean, you know, normally in the combustion engine that comes from the carburetor somewhere. Yeah. Well, okay. Yeah, but okay. This is maybe I think we need to talk about combustion engine a little bit more in detail. Let's
Maybe,
focus this. Yeah,
Let's
but
focus this,
essentially, the different flow, has to come from here as well.
It's
you know.
it's come
And then you're adding air, obviously, in the combustion engine as well. Okay, yeah, and
Yeah,
that's
yeah.
where the okay, now getting it right. I think we need to talk about combustion engines. Okay, but yeah, thanks for so more steady flow on fuel cells and much more dynamic.
much
flow
more dynamic on the
okay.
on the engines.
Yes.
And this is a test criteria or test scenario what is standardized
Yeah.
for the combustion engines.
Yes.
And it's endurance test.
Yeah.
What we did, so we had 100-hour operating in a worst case scenario. So means we had to go from 0 to 100 performance level.
Okay.
So and as you can see here, so we did the measurements for after 19 hours testing and after 100 hours
So
testing.
this is basically the varying outlet pressure that you were
Outlet,
supposed to give.
yeah, to give.
Give coming
Yeah.
with an inlet pressure.
And you have a time, and you see here also some response times. And the regulation times, and these pink or magenta line is the optimum line.
Okay.
And the performance of the component through the tests, also in a climate chamber, from beginning from -40 up to 120, you see that you are directly following the optimum one.
Okay.
So even also after 100 hours, means that this component is ready to operate, let me say, 15, 20 years.
Okay. So that 15, 20 years of this running, and that's pretty impressive, Waldemar. I wanted to ask you, and I don't know whether you have this, but so I mean, these are pipes and so on. Do you need any cooling or heating on this? Any thermal management at all?
So you need the thermal management itself in the hydrogen systems.
Yeah.
For sure.
Yeah.
So that's why I told you that we have some temperature sensors in the component to see where is the temperature going.
Of the gas,
So is it rising up or is it cooling down?
Yeah.
So because the fuel cells itself, they have also optimum temperature to work.
Okay.
And if the gas is heating up, then the performance level of the consumers, let us say that day, the engine or the fuel cell, it's going down. So that's why you have to monitor it.
Okay. All right.
We make the systems less complex. As an example, we had a project where we optimized the system architecture of a truck.
Yeah.
So, and we reduced the numbers of components at first in the sketch from the 41 to 25. So by using the parallel charging unit, our pipes, and also the high pressure regulator unit.
And this truck had, so this is an actual depiction of it. It had 4 tanks.
No, it's just a sample.
Yeah.
So how the system can look
Can
like,
look,
and that we are worked on a track.
All right. Okay.
So
And so reducing the interfaces essentially happened through introduction of this
of this component, and also by using the HPRU or parallel charging unit, because normally or usually you are doing the joints via other interface designs and common, let me say, common features at the moment in the hydrogen world.
Okay, cool. Wow. So noise we've talked about, flow we've talked about, and yeah, so I think it's pretty interesting to see that you guys are bringing out something to, let me say, reduce the number of components on that whole hydrogen supply system. So actually, ladies and gentlemen, hydrogen supply system is getting easy. That's it.
That's it. That's it.
So how do you see things developing in this area? What's your outlook?
So our outlook is to bring the system to the really safe and less complex level.
Yes.
And this is our passion, and also to optimize the component itself.
Okay.
So the quality is focused on the DNA.
Yeah.
DNA in our veins.
Actually, I to be honest, when doing a little bit of research about Poppe Potthoff, it was quality that I think the Mr. Poppe also brought up first. Yeah, and that's what you reckon. Anyway, I must really say this is super interesting for me. And I think for everyone else, because I mean, you know, by just lowering the number of components needed in something as previously complex as the hydrogen supply system, you're making a great step for the industry, and I think this has been really insightful. So thank you very much, Waldemar, for coming along and bringing your whole entire hydrogen supply system with you.
Yeah.
I wish you well. As you do this and as you implement it, and maybe we can even do a video of where this is actually working in a system. But I think this is something we can call future music.
Yeah.
Thank you, Waldemar, for coming. Thank you guys for watching. It's been an absolute pleasure. If you like this, or if you're looking for components like this, you can find more of them on Hyfindr.com, where you can get in contact with people like Waldemar. And yeah, keep building good stuff in the hydrogen economy. Follow us on our YouTube channel. Have a look at the other videos around. Waldemar's colleague was also there talking about the valves, on-tank valves. And yeah, we wish you well. Thanks for watching. All the best.
Thank you very much.
Thank you.